Hello everyone, welcome to the second day of coronavirus lecture. I think I've improved a little bit. I have a compressor on the microphone so we don't hear a lot of background noise anymore. There's a number of improvements that have been made. It's good stuff. Alright, so I guess the question is, what do we want to cover today? And I threatened to cover recursion on Monday, and I didn't do that. So today I think we'll cover recursion, and I'll talk about 2D lists. The dog cam is coming. Currently I don't have a webcam hooked up, but as soon as I do, there will be a dog cam next week. So that just gives you another reason to tune in next week for a new exciting episode of cs201. All right, so let's begin by discussing a little bit about what recursion is. So yeah, I guess we can just jump right in. Let me make my font a little bigger so you guys can see it maybe a little better. Let me define a function. There we go. What are we going to put in this function? I think what we'll do is we'll make the function take a variable x. And then what I'm going to do is two things. If x is equal to 0, we can return, we can return 1. Else, why don't we return test function of x minus 1. Now, of course, this might ignore the possibility that x can be negative or a string or something like that. Let's ignore all those possibilities. Let us assume we enter a positive or at least non-negative x. Okay, what happens when I call this test function? And every time we go into the test function, let's print out entering test function. All right, Portal 2 stream. I actually have to probably reinstall Portal 2. It's been a while since I've played. That's all I can say about that. Okay, so what happens when we call this function? So name equals main. Let's call the test function on 5. So I'm going to show you how I'm going to use the debugger here. The reason why I'm going to use the debugger is so that it'll allow us to look through how the functions are executing one after the other. So let me so when you click on run, instead of clicking on run, you just click on debug. And then here's the console. So let us, I think we want to step into this function, step into this function. And then, so here, let's look at the console. So what's going to happen? So after the print statement happens, it's going to print out entering test function 5. Right. Now we see that x is not equal to 0, x is equal to 5. So it's going to skip over this if x equals 0, and it's going to go right to the else. So it's going to go to here. And you see that the debugger has noted that we are in the function where x is equal to 5, because x colon 5 is written up there. Okay, so now what happens? When we step in, it's going to return the test function. But what it's actually going to do is call the function again. So now you see it's changed. X is now equal to 4, right? And now, of course, we'll print entering test function 4. And then is x equal to 0? It's not. So it's going to jump and return test function 3. So let's see. Yep, return test function 3. Finally, it's going to try again, and it's going to return test function 2, test function 1, and then test function 0. But now what happens? What happens when we return, when we get to test function 0? Well, what we're going to do is we see that finally this if statement actually activates. So we will, or evaluates, I should say. So we're going to go and return 1. So the real question is, what's actually happening here? And let's see if we can see it in the debugger. What we see here is we have one test function that's sitting at line 7. It's about to return 1. And then we have 1, 2, 3, 4, 5 test functions. And you see them here, each waiting to return based on what this one returns. So what we're doing here is this function is the test function with the parameter 0. And what's going to happen is it's going to return. And then what we'll see is that this top test function is going to, what we call it is pop off the stack. And so let's do that. So now that test function is gone. And so what test functions are left? Well, we have a test function, and let me see if I can get it to not scroll, or maybe I can get it to do this. So yeah, there we go. We have a test function with the parameter 1, we have a test function with the parameter 2, parameter 3, parameter 4, parameter 5. They're all just waiting. Each one of them is waiting. Well, test function 1 is waiting on test function 0, which just finished. So the next thing that's going to happen is it's going to return, and we're going to see one of these test functions, the top one, where x is equal to 1, it's going to return 1 again. Everything is just going to return 1 because our base case here is 1. So there we go. We see one fewer test function on our little stack. There is a truck going by or something. Sorry about that. Okay, so now we have test function with x equals 2. And so what's going to happen now is test function 2 is going to return. And then what we're going to be left with is test function 3, which is sitting at its return, waiting to happen. And then we'll do that. We'll return that. So we get test function 4. We'll return. And remember that at every point, this is always returning 1, because the first base case is returning 1. These can only return something that's already been returned in the past. It could return anything else in the first case. We'll make it something more meaningful in just a second. So this is a stupid test function, but I'm just trying to get you guys on board with the idea that you basically have the same function that's sitting around, and many versions of them are waiting for the last one to finish. And when the last one finishes, then the next to last one has to finish, and then the next one, and then the next one, all the way back up until you get to the first one that you called. And so here currently we are at test function, I think it's, yes, if you can even read that, I think you can actually read that a little better than you could in lecture. It says x equals int 4, so that means that we're in test function 4. We return one more time. Now we're in test function 5, which is the first one we called, right? That's the one that our if name equals main is calling. So what happens now? So we return one last time, and now we're back at test function 5. Now I don't have it printing anything out, so at this point, this function is just going to end, and our program will end. There we go. Program over. All right, well, it wasn't that exciting. I expect the answer to that is not really. So let's make the next thing that we can make. So let me show you. Let me see if I can do this in a way that is good. So I'm going to go to here. And so let me just talk about factorial. So I assume that most of you have seen factorial before, but in case you haven't, let's define factorial. And of course, if you've seen my 203 lecture, then you know that I'm using the same thing for that one. Okay, so what is factorial? So factorial is basically something where if I say it's 5 factorial, for instance, this is equal to 5 times 4 times 3 times 2 times 1. And if we have something like 7 factorial, we have 7 times 6 times 5 times 4 times 3 times 2 times 1. And so you can kind of see what we're going to do if we want to make a recursive function. So a recursive function is something where the function calls itself. So that's the general definition of recursion, is if the function calls itself, then it's a recursive function. If the function never calls itself, then it's not recursive. There's really two pieces of a recursive function. There's the base case, and there can be multiple base cases. The base case is how you stop the recursion. And then the recursive case are where you call the function again. Okay, so there's one more thing to say about factorial before we go on, and that's that 0 factorial is just defined, so you can consider this a definition to be 1. There's reasons for this that I'm not even going to really talk about. Just suffice to say that it makes formulas work out properly. If you don't do this, things won't work out as nicely. Okay, so how can we make, let me see if I can make a new page. So how can we make a factorial recursion? And so the answer is, what we're going to do is we're going to have a factorial function. And so here's our function fact, right? So I'm going to do this in kind of pseudocode. I'm going to say either x is equal to 0, in which case, in what case will we need 0 factorial in code? The answer is if you're implementing a factorial function that you expect will be used by someone who is a mathematician, or by someone who doesn't know that you don't care about 0 or something like that. So basically the point is that you have to implement the 0 as the base case. And so what we can do here is if I tell you that x is equal to 0, you're allowed to just return 1 to me. And in that case, this is not a recursive call. This is a recursive function, but this is not going to be a recursive call because in the base case, we don't call the function again. So now I want to talk about what if x is not equal to 0. So really, if x is bigger than 0. So if this is the case, then we go this way. If x is bigger than 0, then we're going to go this way. What are we going to return? Well, we want to call the function again, so we don't know what x factorial is. We're going to return x times the factorial of x minus 1. And let me justify this to you. So basically what I'm saying is that 5 factorial is equal to 5 times 4 factorial, which is then equal to 5 times 4 times 3 factorial, which is equal to 5 times 4 times 3 times 2 factorial, which is then equal to 5 times 4 times 3 times 2 times 1, technically factorial. Finally, this is equal to 5 times 4 times 3 times 2 times 1 times 0 factorial. And once we get to 0 factorial, we know we're in this first case, so we can return 1. So, okay, let's jump back to the code and see how much progress we can make. There we go. So for any non-negative integer, x factorial is equal to x times x minus 1 factorial. That is 100% true. So yes, you can say it like this. Like that. And so, okay, let's implement this. Let's define our factorial function. And factorial, in this case, let's just take x, because I've been saying x that whole time. If x is equal to 0, we return 1. So you see in this case, well, first, okay, there we go. We see in this case it's almost identical to this test function. The only difference in the code is going to be in the else statement. We're not going to return just fact of x, or fact of x minus 1, I should say. We're going to return what? X times fact of x, right? Because that's the definition that we've just written here. N factorial, or x factorial, is equal to the first one stripped off times the remainder factorial. And if you're saying, yes, that would not work if x equals 0, the formula doesn't work for x equals 0 because it's a special case and it's defined differently. Okay, so now instead of factorial, instead of the test function, let's call fact of 5. So what is fact of 5? So if you actually know what 5 factorial is, it's 120. So let's just make sure that it actually turns out that way. Let me just print x times, or let me just make this function a little bit more complicated. And so in real life, you don't need to do this. The only reason why I'm doing this is so that we actually can see what is happening at every step. And you'll see what I mean when I run the debugger on this. So let's run this program, debug this thing. Okay, so here we go. Let's step into the function. So you see that we have factorial where we're setting x equal to 5. So now we are going to go to this part. We are going to set y equal to x times factorial of x minus 1. And so how are we going to set it? So the thing is, like, in this equal statement, in this assignment statement, we have a function evaluation, right? And so because we have a function evaluation, we can't just set y. We have to evaluate fact of x minus 1 first. So what are we going to do? So we're going to step into that line, and now you see x is equal to 4. And you see that down here in the debugger, there is another fact function that has been started up, right? So this fact function has x equals 5. This fact function has x equals 4, and it hasn't evaluated yet. You see that this one is at line 17. It's waiting for this assignment statement to complete. Here, it's sitting at this if statement. This if statement's not going to evaluate as true, but we don't care. Now it's going to jump to the same line, and once it jumps to the same line, we see that x is equal to 4, x minus 1 is equal to 3. So then what's going to happen? It's going to call it again, right? And so I know that I said that a recursive function is something that has to return itself in its call, or it has to call itself. Here's where the function calls itself. I don't care if the function calls itself in the return statement, though you see that that's actually kind of what it's doing. We're assigning y, which is just a stupid dummy variable, and then we're returning y. Okay, so let us call it again. So now you see that instead of doing 4 times 3 times 2 times 1, it has to jump into factorial of 3. So the next thing it's going to do is give us fact of 3. There it is. And so what we do now is we say, what is it going to do next? Well, same thing, right? It's going to skip this if statement, or I shouldn't say skip. It's going to evaluate it as false, so it's going to jump to the else. It's going to jump to line 17. You see that all these, this is fact of 5, fact of 4, fact of 3. They're all waiting at line 17 because line 17 is the recursive line. It's the line that causes you to call the function again. And so now what we're going to do is we're going to call it on fact of 2. Jump to the same statement, call it again, fact of 1. Jump to the same statement, call it again, fact of 0. Wait a second, right? So at this point, we're down to what we call the base case. And so when we get to our base case, you see that it's going to evaluate where? It's going to jump to this return 1 statement. And now let's watch as it unfurls. So you see here, this call is going to terminate on line 15 rather than on line 17. So we basically see that line 15 here, or line 14 and 15, you might call those the base case in this case. Lines 16 through 19 or whatever you could call the recursive case. All right, so yeah, I'll even write that in. And then I will hit that. Okay, so let's jump out of this function. We're done with the base case. We've got our number 1, so we can return. Fact is in front of x minus 1 because fact is the function that we're calling on it. So what we're saying here is multiply x times whatever comes out of this same function, except instead of putting in x, you put in x minus 1. So, okay, let's jump out of this function. There we go. So now we're back up. So what you saw was that one of the facts disappeared. And we have, at this point, we're at x equals 1. We are saying y is equal to x times fact of x minus 1. So remember, fact of 0 returned 1, right? And x in this case is 1. So y is going to be, oh, let's see if I can even, oh, it doesn't know yet. Let's do this. So y is equal to 1, so we can print it and then return it. So if we look at the console, we'll see that we've printed out 1. So 1 was the first result from the recursive case because we got fact of 0, which is 1. 1 times 1 is 1. And then we printed out 1, and now we're just about to return it. So let's do that. When we return it, where are we going to go? We're going to go back up to fact of 2. So let's do that. There we are. So now you see we're at fact of 2 because here x is equal to 2. Remember, fact of 2 is hanging out in this line 17. All of the other facts, if you look at them, this one is hanging out at line 17. This one is hanging out at line 17, line 17, line 17. They're all hanging out at line 17, waiting for the result of the previous functions to come in. Basically, it's like a game of telephone or something like that, where you basically have to send the message down the row of people, and then the message the answer to the message comes back. So in this case, x is equal to 2. Fact of x minus 1 is equal to 1. So 2 times 1 is going to be 2. So it's going to return. It's not only is it going to print 2, but it's going to return 2. And so when it returns 2, it's going to return it up to fact of 3. Here we go. So now here's the first place where it becomes a little interesting. Factorial is not just like 2 factorial is 2, 1 factorial is 1, 0 factorial is 1 by definition, so that's probably not very interesting. Here's the first factorial that's actually kind of interesting. So 3 times 2 is now 6. So you see that now it's starting to grow a little faster than just x. So y is going to be equal to 6, right? This is in fact of 3. So 3 factorial is 6, and then it's going to return itself up to fact of 4. And the thing is that every time you return, you have to remember. So now you see we're in fact of 4, right? X is equal to 4 here. So x is equal to 4 here. We're sitting in this line, right? We were waiting for fact of 3 to return. But now I know what fact of 3 is. Fact of 3 is equal to 6. So now what we can do is we can say this is 4 times 6, which is 24. And so then what we're going to do is print 24, or I guess assign y to 24, then print 24. And so you see here we've printed 24. And now we're going to return. So let's return. And we're finally back up to fact of 5. So fact of 5 is going to do the same thing the fact of 4 did, except it has to remember that fact of 4 was 24. So fact of 4 was 24. We're at this line, so we have 5 times 24. As it turns out, 5 times 24 is 120. There we go. And so we return there, and then we are finished. So that completes our sample run of factorial. So if we're going to print this out and say fact of 17, and then let's say we just run it instead of debugging it, then what we see is that at every stage it's going to print out 1 coming out of fact of 1, 2 coming out of fact of 2, 6. Why would you use this instead of a loop? The answer is it's way better to use a loop for factorials, but this is the simplest example of where you do something interesting with recursion. So the vast majority of the examples that we're about to teach in terms of recursion are things that can be done more easily with loops than with recursion. But recursion itself is hard, and so we're using easier examples to get into them. The one thing that recursion is extremely useful for, and maybe I'll just draw it out, and I'm going to do an example of this in a second. So, but I'll show you that example. But really, basically anything where you have to make a decision. So if you have, say, you start here, and you can either go left or right. And so if you go left, you can, and you're now at, say, position 1, and here you're at position 2. And so you can either go etc. until maybe you reach the end here. Maybe you can go left and right one more time here, etc. Maybe this is some kind of, for instance, like last semester, maybe this is some kind of maze. To actually go through. Oh, sorry guys. Huh. There we go. Sorry. Pure white screen. Excellent. Let me get rid of all of this. Start over. So basically anything where you have to go left or right. And let's say that this is an end. Let's say that this is end. You can go left here, right here. doing this kind of behavior, this is actually what in computer science, we call this tree. This is a tree structure. And I'm not going to say that we can't do anything with a list. I'm sorry, a loop. But recursion is basically infinitely better. In this case. So basically this is one of the first examples, and I'm going to show you an example pretty soon where actually we do this exact type of thing. Anyway, let me go back for just a second to the factorial problem and show you the actual like loop way to do it. So cool. Let me get rid of that. Okay. So someone tell me why I made this 1 to x plus 1 rather than just doing, I guess the question is, why didn't I just do range x? Yeah, so basically you're both right. The first thing is if I accidentally used range, so the thing is, if you do get a start and a stop with range x, right? It just starts at 0 and it goes up to x minus 1, which is not what I want. But the reason why it's not what I want is, you see here what I'm doing is I'm multiplying the total by x. Right? Yeah, exactly. So it would stop at x minus 1. So that would compute x minus 1 factorial, not x factorial. So that's the first problem. So that's why I have this upper end as x plus 1. So here's the question. Why do I have the lower end as 1? Look at this statement and tell me what the problem is. If I was allowed to put a 0 into x, what would happen? What would always happen? And while you're doing that, I'm just going to do yeah, so the answer would end up exactly. We'd get a 0 times this 1 in our first step. And, oh, shouldn't have done that. Look at that. There we go. Fixed. That would have been an interesting bug. Anyway, okay, so let's enter a number. The number is going to be 13. And so what we see here is, oh, I'm sorry. Try again. There we go. We see that in both cases, this loop and this recursion give you the same output in terms of what the final function returns. Here's the question. Which one will run faster? Will the recursion run faster, or will the loop run faster? And while you guys are thinking about that, I'm going to talk about a new example. Yeah, so which is faster? Yeah, so so Dennis didn't get tricked. This whole question was a trick. The loop is definitely going to be faster. The reason why is because every time you call a function, Python has to create a new instance for the function. It has to copy all the variables. It has to basically make a new place for all of the calculations to be done. So, so basically recursion, if you can avoid recursion, the answer is to avoid recursion, because normally recursion is slower than non-recursive solutions. On the other hand, if you can't avoid recursion, or if recursion is definitely the best solution for a particular problem, then you're stuck. And so here's an example. Let me just give you an example. So let's talk about rabbits. And you see it's not blank this time. It's not blank this time. So the tree example is an example where you would need recursion, right? That's the reason why I was talking about it. So let's talk about rabbits, otherwise known as the Fibonacci numbers. And so here's an example where you can do this without recursion. You can. But it's actually a little less obvious, so let's show you what the Fibonacci numbers are. The Fibonacci numbers are, we define f0 as 1, we define f1 as 1, and then we define f sub n is equal to f sub n minus 1 plus f sub n minus 2. So this recursion essentially writes itself, because you see that this is a sequence, like a mathematical sequence, that's defined recursively, right? F of n is defined in, yes, it's defined in terms of the two previous numbers. And so given that it's all defined in terms of the previous numbers, let me get rid of all this crap. There we go. We can write a recursive function. So basically what you're going to do is when you write your fib function, fib of n, you're going to say, well, if n is less than 2, we're just going to return 1, right? Because, I mean, let's just pretend that f minus 1, f minus 2, whatever. If you even want to consider these defined, let's just say that they're 1 as well. So everything going back, if you want to consider those as defined, we'll just return 1. This is a way to keep users safe from accidentally doing some naughty things. Okay, so what if, now we're in the case if n is bigger than or equal to 2. What do? Right? We want to return Fibonacci of 0. So I guess it depends on how you define it. You need 2 ones to start. That's the point. So I don't care if you call this f of 1 is equal to 1 and f of 2 is equal to 1, and then your next one, f of 3, is equal to f1 plus f2, or if you start where I did, where I have f of 0 and f of 1. So the difference is really just a shift of the indices by 1, so that it doesn't matter. The important thing is that here we know what we're going to have to do because we have the definition already. So we are going to return fib of n minus 1 plus fib of n minus 2, right? I mean, yeah, again, as I say, in terms of the indexing, it doesn't really matter. I mean, if you define f0 as 0 and f1 as 1, then f2 is going to be equal to 0 plus 1 equals 1. And so basically what you would be, so let's put hats on these. So basically what you're saying is that f hat n equals fn plus 1 or something. Okay. All right. Cool. So we're going to return this. Now, the issue about this is that we see that there's actually 2 recursive calls. So the way that this is going to work, and let me start a new page, is that if we have, say, fib of 4, it's going to call fib of, let me just, instead of writing fib a whole bunch, I'm just going to call it f. So f of 3, and it's going to call f of 2, and then it's going to add them in the end. But f of 3 is going to have to call f of 2 and f of 1, right? And then f of 2 is going to have to call f of 1 and f of 0. F of 2 again here is going to have to call f of 1, and it's also going to call f of 0. So here's one inefficient thing about the recursion that we're about to write, is that you notice that there are multiple calls to the same function going on. Because over in this call, when f of 3 calls f of 2 and f of 1, it doesn't remember the result after f of 3 returns. So once it goes into f of 2 again, it's going to say, I don't really remember what f of 1 is, so I have to recompute it. I don't remember what f of 0 is, so I'm going to have to recompute it. And I don't remember what f of 2 is, so I'm going to have to recompute it. So this version of our calculation, where we just do this easy two-step process, is going to result in a lot of multiple calculations. So let's just define this function and see what happens, right? So actually, let's just define it and see what happens. Oops. Okay. Oh, there we go. So there we are. So our Fibonacci function is defined. Basically, what we have to do now is, let's actually just put this in a while loop. While x is not equal to, say, -1. Print fib of x, and then we will input this again. This is just so that we don't have to keep restarting the program every time. Okay, so let's enter a number. Let's enter fib of 4. So before we enter fib of 4, let's actually just compute it. So what is it going to be? So it's going to be fib of 3 plus fib of 2. Fib of 2 is 1 plus 1, which is 2. So fib of 3 is going to be 3. So fib of 4 is going to be 5, unless I'm mistaken. So let's see what happens. There we go. So what we see here is that we haven't learned anything. Maybe what we'll do is we'll say x equals fib n minus 1, y equals fib n minus 2. There we go. And now instead of recalling it again, we can just return x plus y. So we're doing the same kind of modification to this function that we did to this function, just so that we can see what's going on. So let's rerun the program. So let's run it on fib of 5. So if fib of 4 was equal to 5, then fib of 5 is going to be equal to 5 plus 3, which is 8. So let's see what prints out when we do this. Okay, so what happened? We see here, first, fib of 5 calls fib of 4, which calls fib of 3, 2, 1, and 0. And then it goes back up. And here, at fib of 2, we have to call 1 again. Oh, actually, I'm sorry. This is at fib of 3. Which we'll call fib of 1. And so we see that there's a bunch of calls that happen repetitively. So actually, why don't we just debug this? I think that's probably the smart answer. So let's call it on fib of 4. Oh, I'm not debugging it, I'm just running it. So let's enter fib of 4. So now let's step into the function. So we see fib of 4. So here it's going to call fib of 3. But you see that what happened? here it got to this part of the function. It never called fib of 2 yet, so we have to wait until it does that. So let's track to see how this works. So here it's calling fib of 3, then it's going to call fib of 2, then it's going to call fib of 1, and then it's going to call, oh, I'm sorry, right. So fib of 1, since 1 is less than 2, it's just going to return 1. At that point, once it returns out of here, but where are we? So we're at fib of 2, and it's finished calling fib of 1. So now we're going to call fib of n minus 2. So that's 2 minus 2, which is 0. So when we call it on that, we're going to see n equals 0 again. And then what we're going to do is it's less than 2, so it's going to return 1. And now we're at this line again. But so where are we? We're back at n equals 2. So if we go over to our little thing and we look at fib of 4, then where are we? So what we did was we just hopped down here, we hopped down here, we hopped down here. So we've hopped back up to fib of 2, we've hopped down to fib of 0 again, and then back up. So right now where we're currently sitting, this is where we are. And so the point is that what we're going to do now is we're going to return out of here. We're going to go back up to fib of 3, and fib of 3 still has to call fib of 1 again. And that's what's going to happen. So let's look at this example. So let's do this. So what happens? So we're going to 1 plus 1 is 2. And so here we're at, so notice here, we are at fib of 3, right? So because n is equal to 3. And so we already called it on fib of 2. So it's going to drop down to this next statement. It's going to print out calling fib of 2. It's going to call fib of 1. And then it's going to call it on fib of 1. So there we go, fib of 1. It's going to return 1. Okay, so now we have y is equal to, if you look at what we have here, we have x is equal to 2 and y is equal to 1. So now it's going to return 2 plus 1. Yes, wrong screen. So it's going to return 2 plus 1. Okay. Once we return 2 plus 1, where are we? We're at fib of 4, so that's the biggest one. But then if we hopefully look over here again, so now once we've returned from fib of 3 was equal to 3. And so over here, now we're going to go down this side. But the thing is that this fib of 2 doesn't remember anything from this side, so it just has to repeat all of these calculations. They must be repeated. And so that's what's going to happen. So let me try to go back here. So now what's going to happen is we go into, so here now we're going to call it on fib of 2. And here we're going to call it on fib of 1. And then there we go, fib of 0. And then finally here we're back up to the fib of 2. So now after clicking a whole bunch of times, where are we again? We are at f of 2. So at this point now, this is where we are. We're right here. So fib of 2 is equal to 2. And so finally we can compute fib of 4, which is equal to 3 plus 2 is 5. So that's the last step that we're going to do. So let me jump back. And here we go. So once I click this one more time, we'll get to the return statement. And then once I click this one more time, you see that there's only one more fib left after I do this. There we are. So now we're at fib of 4. And so there we go. We know now what fib of 3 is and fib of 2 is, so now we can call it on x plus y and return. And so there we go. And so at this point, I guess what we do is enter -1 and the program ends. let's see. Let's get out of here. This seems absurdly complicated. I suppose. Okay, so, cool. So, you might be thinking, is there a better way to do this, maybe with loops? And there is. So I guess really what we want to do is say if and then we can have f previous is 1 actually I think we don't need that, we can just do it this way. We can say f prev I guess current. And then what we do is we say, okay, now and we can return current. So this is kind of the loopy version of it. Anyway, okay. I don't even want to really run this. What I want to do now is I want to talk about the simplest possible tree problem that I can give you. So this is doing some kind of Fibonacci tree recursion, but you don't need to do it. You can do it with a loop. Here's a problem that if you can do it with a loop, I'll give you +2 extra credit points or something. But don't waste time. Okay, do not waste your time on this. So what I want you to do, or me to do, I guess, what I want to have done is I'm going to give you, I say, a length. Say the length is 4. How do you send your solution? If you have a solution, you should email me. Because my assumption is that most of you will not come up with a solution because I don't actually have a solution to this. I think, I mean, I guess I could probably come up with one, but again, this is a joke. So say I say length 4. What I want is all the combinations of A's and B's that you can write down. So for instance, something like this: A, B, A, B, A, B, B, A, B, A, B, B. Oh, I just came up with the looping solution. So, and of course this is ABBA. And then basically we get all the same things. We get ba, Bob, Baba, Bab, Baba, and then we get, and finally, maybe I've just written bigger or something. What have I done? 1, 2, 3, 4, 5, 6, 7, 8. So that's right. 1, 2, 3, 4, 5, 6, 7, 8. So that's right. So there are 2 to the n of these. Well, the point is, so the point is here, I want you to be able to write all these out. And so now I'm going to show you a recursive solution for it. So here's my idea for a recursive solution. My recursive solution is going to be, if you go left, that's going to be an A. If you go right, that's going to be a B. Okay? And so what we're going to do is we're going to say we want to build this tree structure to a depth of 4. So here we want it to go and finally, etc. So yeah, you have, I guess I can write it out, though it's kind of squished. Okay, so how are we going to do this? Well, what I want to do is I'm going to it does not matter, the order doesn't matter. But if you do it with a loop, you can actually do it in the same order. But the point is here. Here's the point. If you do this, then what we're going to do is we're going to have a partial answer. So we're going to have a partial answer. And so what we're going to do is, as we go down this way, we're going to say the partial is equal to A. And then as we go this way, we're going to say the partial is equal to AA. Then AAA. Then AAAA. We're also going to have a counter. So the counter here is going to start at 4. The counter here is going to be 3, 2, 1, and 0. When the counter hits 0, we're no longer going to branch. So that's why we don't go down to another A and B down here, because the counter has hit 0. So we're going to track how far we've gone down. We're going to track how far we've gone down, and then we're going to stop whenever our counter hits 0. All right. So how are we going to do this? Well, let me show you a potential answer. And I guess if the counter hits 0, we'll just print out the answer. So, all right. Let's define a function. Def A's and B's. And what I'm going to do is I'm going to call this partial. Oh yeah, you're right. Thanks for reminding me. I'm still getting used to this. It takes a lot. It's more multitasking than actually just being in a physical thing and teaching in person. Okay. So what I'm going to do, and let's get rid of this now. Let's just call A's and B's on length 4. And in this case, I'm going to start with the partial is empty. The reason why I'm starting with the partial is empty is you notice that we're going to start with no A's or B's. Okay, so if the length is equal to 0, then we're going to print out partial. And so what you're going to notice here is that we're not actually returning anything in this part. So this function is not going to return anything, but I'm also not going to care about that. Else, actually, technically, if you want to be uber safe, you can always do that, just to make sure that if some crazy user enters in a negative number, you don't go forever. Is there a lot of interference? Huh. All right, hang on. Okay. I muted the mic. Hopefully it let me turn down the volume just a little bit. Maybe it won't feedback as much. Well, I have a low band filter on this. Yeah, I'll have to listen to it and see if I can fix it at some other time. Yeah, I'm sorry, guys. Okay. So, yeah, I assume it has something to do with feedback, though I'm on my microphone and I'm on headphones, so it shouldn't be feeding back directly. Don't ask me. The headset does not have a mic. It's just headphones. So there really shouldn't be anything. It could be... I don't know. Okay. Well, anyway, I'm curious if this function works. Let's see what happens. Okay, so let's see what happens when I call this function. So let's see what happens when I call this function on just 1. Cool. A and B. Are we shocked? We are not shocked. Let's do it again on 2. So as it turns out, my phone is close to my computer. Oh, you know, I wonder if my phone, my writing tablet is sitting on top of my phone. And I know that phones do sometimes cause random interference. So, okay. Tell me if it's resolved now. Okay, but anyway, the more let's ignore the random clicking and clacking, and hopefully, and pay more attention to what's actually happening here. Yeah, what does the partial parameter do? So the partial parameter has to remember the answer at each step, right? Because here we see that we're going to print out AA and AB. So the point is that what we're going to do, if we debug this thing, is this. So let's step into the function. We'll step in here. And so you see that the partial is currently nothing, or empty string, I should say. And so then it's going to call with A. So now partial is equal to A. And length is equal to 1. So it's going to call, with partial already equal to A, it's going to call this with length of 0, and partial is equal to A plus A. So it's going to give us AA with length of 0. So now that the length is 0, it'll just print this out. Cool. And then it leaves this function. So now we're back to where the partial was just A. And now we're going to print partial is equal to AB. The length is 0. So we'll print it. Cool. Finally, we jump out. So now partial is equal to nothing again. So now we're going to go into where partial is equal to B. And so now, because partial is equal to B, we have length is equal to 1. So it's going to call it with length is 0, and partial is going to be equal to BA. And so then it's equal to 0, so it'll print that. And finally, now we go back to where partial is equal to b. And here we print out partial is equal to bb. So now we're just popping out of the recursion. There's no more to do, and we are done. So you see that this is, I would say, okay. There we go. And that's an example of me documenting my code for no particular reason. All right. So there is a way to do this with loops. I think. Yes. I'll see if anyone can think of it. I think it's a bit of trickery. And it has to do with binary, which I haven't taught yet because that comes up in future lectures, which is why I think that it might be a little difficult. Anyway, let's do a's and b's of 8 and see what happens. And let's just run it. There we go. So here we are. Here's all, I guess it's 2 to the 8, so it's 256 possibilities. All right. Let's do one more, maybe at least one more example. I want to do one more example for various reasons. So this is another, I guess A's and B's are not really mathematical, but this is also a non-mathematical example. So what is a palindrome? So a palindrome is a word that is the same forwards and backwards. And of course, you've already done a lab on it. You've already seen a homework on it. Yes, race car. Of course, no space. Apparently taco cat. What else? Yes, you've done this for homework, but guess what? All that is old is new again, and you're going to see this again. So the point is that okay, the point is there's a giant truck driving by, but other than that, okay, too bad I hit a boot. I think that is, yeah, looks right. So we're going to write a recursive So, first things first, what does pass do? I actually caught it that time before I saw the comment, so I get to pat myself on the head for that one. So, as it turns out, pass does nothing. But the point is that this is a function, right? And functions expect that there's going to be code that's tabbed in on the next level. Yep. And so, because it's expecting code to be tabbed in on the next level, something has to be at that tab level. If we don't have this, you notice the PyCharm is going to be a little bit angry. It gives us this red underline. It doesn't like it. So if you put the pass in there, the function won't do anything, but at least you know that you can run this code and it won't give you an error. Pass is totally legal in this class, but if we find passes in your code, what that means is that you forgot to take a pass out, right? Pass just means it's a placeholder. Sometimes you'll see pass in real code, but for you, if you ever use pass, make sure all of your passes are taken out by the time that you actually finish your code. Anyway, I was just doing it to avoid errors. Cool. So now let us call recursive palindrome on TacoCat. And we can call it on what is that one? I'm just going to copy paste some of the stuff from the comments. So those are things that are palindromes. There's something that is almost certainly not a palindrome. No comment, Max. Oh, Tibbet. That's actually a word, I think. Okay, so anyway, let's actually write the recursive version of this thing. So let me show you an example of how to write the recursive version of this thing. So what we want to do to a word, if it's a palindrome, so if the length of the word is in 0 or 1, now this is the most I shouldn't say most, this is a silly way of saying but I'm lazy, so whatever. We're going to return true. We are going to consider all single letter words and the empty string are palindromes. And that's just for the sake of sanity. I mean, technically we could say that a single string isn't a palindrome, but then we couldn't really do this recursively. So what if the word's length is bigger than 1? Well, what we want to do is we want to compare the first element to the last element, right? We want to say if the word, and I'm going to do this without negative indices or anything. I'm going to do this just with positive, so is equal to the word at length of the word minus 1. Then it could still be a palindrome. Else, it's not. We found 2 letters that don't match. So we will return false. Okay, but if it still could be a palindrome, then what do we want to do? And so here is where I'm going to use slices. So what I'm going to do here is I'm going to return is a recursive palindrome on the word, and so I'm going to use a slice. So I'm going to start at, instead of starting at 0, which would be the first letter, I'm going to cut off the first letter, and I'm going to cut off the last letter. So you remember that so slices return up to the last index, but not including it. So basically the way that we look at this thing is, why don't we print it out before we call the recursive palindrome on it. Okay, so let's do this. So let's comment most of this out so that we don't end up with a literal avalanche of output. Now I'm going to run this. So what we see here is the first thing it did was it looked at TacoCat and it said, the t at the front is equal to t at the end, so it prints a coa or something. And so then it calls it again on the sliced thing. And so the next sliced thing is just ACOCA, and it's not small enough yet, so it checks it and it says A is equal to A. And so then it'll slice it off again, so we get COC. And then it returns it again. So then we go back up to the word. And C is equal to C, so it strips off the C's, and we just get O. And then finally what it does is, once it gets to O and it calls this function again, the length of the word is actually just 1 now. So length of the word is either 0 or 1. So now what it does is it just returns true. So basically, I'm going to post this on the GitHub, and I suggest that everybody kind of look at it. Yeah, so let's look at another one. Oh, false. I guess I copied something wrong, or something happened that was wrong. Pine. P-L-E-E. I'll have to look at that one. Oh, there's a space. Yeah, it's the space. So we see here that what happens is it agrees on the P's, I, N, E, A, P, P, L, and then once it gets down to 2, it strips it down. We see that there's this extra line here where it calls the recursive palindrome function with an empty word. And that's why we have this 0 in there. So let's just see something that turns out to be false. What's something that turns out to be false? Let's just do the word that. And the word that is good because, actually let's just do double T's on it. So what we see is, it's going to return, oh, I should actually call the recursive palindrome function on it. There we go. So the first thing that it's going to do is it checks this t versus this t, which works. So then what it's going to do is it's going to strip out that outside of it and call it on it. And so this t is equal to this t, so it works. But then it's going to call it on ha, and we see that ha, its length is not 2, or I'm sorry, its length is not 1 or 0, but also its length is, and so it checks to see if the first thing is the last thing, and it's not. So we return false, and then what happens is it returns false, which starts getting returned through all of these recursive palindrome calls, all the way back up to the top. Okay, so I think, if I'm not mistaken, that is it for the day. I've gone a little bit over, but whatever. Are there any last questions? Or do you guys just want to have this code on GitHub so you can run it and see what it's actually doing and trace through it? All right. I'm thinking I might take this as a quasi-formal announcement. So I think we're going to delay. I know that a lot of people are leaving. I think we're delaying the exam until a week after it's scheduled currently. But yeah. Okay, so actually I'm just gonna copy, paste, commit. All right, so it's under online lecture 2. There's a file called recursionlecture.py. All the code for today. Online school continues for the rest of the semester, at least so far as I know. I think Hrabowski said something about that. So, no recursion on Project 1. For the love of God, no recursion on Project 1. If you do, you'll hurt me in the feelings. So, is there a good way to practice recursion? Yeah, I mean, so there's a number of recursion problems that I can probably try to write up over the weekend. All right. Oh, I mean, recursion is totally allowed. Anything that's taught in class is allowed, but I recommend against using recursion on Project 1, mainly because I just don't see how it would help you. I see how it could confuse you and hurt you and cause you to spend a lot more time working on things than you should. I do not see a way that it will make anything easier for you. So we will have recursion on Project 2 most likely, or alternatively Project 3. So one of the projects will have recursion, just not Project 1. All right. And I think with that, I think we're good for the day, right? Have a good rest of your day. You know, go out and get your plague masks. All that kind of stuff. All right. Cool. Bye, all.